Hi everyone, welcome to our fourth lecture. This lecture is going to be on waves, and it is a combined lecture for both the calc and the non-calc students. However, for the calc students, there's going to be an additional lecture where I will go through some mathematics where I derive some of the equations that you're going to see in this lecture, and that derivation, of course, requires calculus, and so it's only appropriate for the calc students. Okay, so what we're going to do in this particular lecture is I'm just going to introduce the concept of waves and describe some of the phenomena that waves exhibit and their formulas without necessarily deriving those formulas from deeper principles, because that derivation is actually quite complicated. Okay, so let's start off by describing what is a wave. Okay, and first, I have to tell you that it's a collective phenomenon, and what that means is it's the motion of many particles, many objects. Okay, it isn't just one object or two objects or a few objects. It's in principle an infinity of objects. So like last semester when we were talking about Newton's laws, we did things like a block on an inclined plane, or maybe there were two blocks and they were attached by a line, a cord of some kind, and a pulley, and there was always just a few. And then when we got to things like conservation of momentum, you might have had like three or four objects colliding with one another and interacting and so on. But when it comes to collective phenomena like waves, what you have is in principle a very large number of particles that are interacting with one another. Okay, and by large particles I mean things that like down to the microscopic level, where you have atoms and molecules that are interacting with one another, and they give rise to some kind of collective behavior. Okay, so like Avogadro's number, a mole, is like 6 times 10 to the 23. 10 to the 23 is a really big number, and if you really wanted to study the motion of a wave right down to the microscopics, you might be talking about 10 to the 23 particles that are interacting with one another. And at that level, you might as well just say it's infinity. Okay, and so that's very different than the kind of physics when we were looking at just a few particles or few objects that were interacting with one another. Okay, and so a wave is really this kind of a collective phenomenon, and what happens is you have one particle. When I say particle, I mean some element of the underlying material. Like it could be a molecule, or it could be just some small element of the material that moves collectively together. But if you want, you can think of it as a molecule. And when this molecule moves, it exerts a force on its neighboring molecules. Okay, and the nature of that force is unimportant. It could be electrostatics or whatever, but then that molecule exerts influence on its neighbors, which exerts an influence on its neighbors, which exerts an influence on its neighbors, and that propagates along through the material, usually called a medium when it comes to waves, and that leads to this kind of collective behavior, which is the wave phenomenon. Okay, like a kind of a simple example of this, not a perfect example, is when you do a wave in a stadium, you've got like all these people, you're watching some sports game and you're sitting in your seats, and one row of people stand up, and then when the people beside them see them standing up, they'll stand up and then sit down, and then the people beside them stand up and sit down, and so each row of people will influence the next row of people to stand up and sit down and stand up and sit down and stand up and sit down. And that phenomenon of standing up and sitting down through the influence through its neighbors will simply propagate across the stadium, and it gives rise to that kind of a cool effect that you see sometimes in sports. Okay, it's not a perfect example, but it's something that a lot of people have seen, and so it might help your intuition a bit. Okay, now what kind of a wave should we be thinking of or picturing in our mind? Well, there's so many things that exhibit wave behavior, like waves on water. Sound is a wave. Light, radio waves, they're all waves. And waves on a string are also waves. And so just so you can fix your mind on some particular picture, let's picture waves on a string. Okay, and so what I have here in this diagram is a wave on a string. So first look at this line, the straight line along here, which I've I've labeled as the x-axis, okay? So you can think of it as the x-axis, but you can also think of it as the equilibrium of a string, okay? So imagine you have a string and you've pulled it tight, and there's no wave on it right now, okay? So you're not wiggling it at all. It's just sitting there straight like that, and there it is, okay? It just sits there. Now, grab one end, and we're not worried about like how it's tied down or anything like that. I mean, you can imagine that it's extremely long, and there's still some tension in it, okay? You grab one end and you start to wiggle it. You start to wiggle one end, and what happens is of course you get this wave pattern like that, okay? So this line that you see here that I'm tracing out with the cursor, this sinusoidal line, is basically the wave, okay? That's now on top of that string, all right? Now what this wave does is it moves down the string, okay? And so you could see here, like here's a crest, okay? So maybe I should tell you like the upper part of this wave, like the top part, just like with water waves, we'll call that a crest, okay? And then the bottom part down here, okay, where it's depressed like that, we'll call that a trough, okay? And if you were to just like ride one of the crests, you know, just follow that crest would move with some constant velocity v, okay? So that's one of the properties of waves, is that this entire pattern, so I was focusing on the crest, but any crest will do that, and even the trough, and the entire pattern simply moves with a constant velocity to the right, okay, or to the left, depending on which way you're looking at this, okay? So just keep moving with a constant velocity. So that's one property of this wave. The entire pattern is kind of like fixed in shape, but it moves to the right with some velocity v, some constant velocity v. It doesn't accelerate, okay? It doesn't speed up, it doesn't slow down, it just moves with this kind of constant velocity, okay? So that is the motion of the collective behavior. Okay, each one of these crests will move to the right with constant velocity v, but that is not the motion of any one of the particles. So over here you could see that I drew this dot there like that. Okay, so you could picture the string as being made up of billions of like atoms and molecules all the way along the string, and they're all interacting with one another through electrostatic forces along here. Okay, and if you were to follow the motion of any one of those molecules, and you could do this very easily in a string, just imagine you have a white string and you put like a little red dot on it or something, okay? So that's like that little red dot right there, and you just watch the motion of that string, of that dot on the string. You'll see that the dot will move up and down. It actually oscillates. It actually does simple harmonic motion up and down. Okay, so it's not that as this collective phenomenon moves through the string, it's not that the molecules are actually moving to the right with a velocity v. Each molecule stays in place on the string, but just moves up and down. It just oscillates up and down like that. But collectively, it gives rise to these crests and troughs which move to the right at a constant velocity v. Okay, so that's a little hard to picture, but again, just imagine that little red dot there, and what's it going to do? All right, it's just going to oscillate up and down, and it really is simple harmonic oscillation. Okay, so the calculus students will see that in the other lecture. Okay, so it'll just oscillate up and down like that. But this one's oscillating up and down. Its neighbor's oscillating up and down too, but it's slightly ahead of the other one, and so it's oscillating up and down. Every single point in the string stays in place but oscillates up and down, but nonetheless together they form this kind of a wave pattern which moves to the right. Okay, so again, that example with the stadium, each particular spectator of the sport is still sitting in their seat. Okay, all they do is they stand up and then they sit down, but at their seat, they're not walking with the wavefront. They're staying in place. It's just as they stand and they sit, the act of standing and sitting is what moves to the across the stadium, not the individual observers. Okay, so that's what this wave phenomenon is. Okay, so one property was the velocity of the crests and troughs of the entire waveform, and it moves either to the left or to the right at a constant velocity v. Another property of the waves is the distance from a crest to its neighboring crest. Okay, so if you measure from a crest here to a neighboring crest there like that, it turns out that distance remains constant as the entire waveform moves. Okay, and that distance is given the name of a wavelength. and it's given the symbol lambda, which is the Greek letter for L. Okay, lambda, like that. All right, drawn just like that. You'll see it in my notes. Okay, and that's the wavelength. You can measure it from crest to crest, or you can measure it from trough to neighboring trough. Now I don't have another trough here, but there's one back here, I guess, somewhere, and then there'd be one somewhere off here, like that. Okay, but if you measure from crest to crest, or you measure from trough to trough, you're going to get the same lambda. Okay, doesn't matter whether you're measuring crest to crest or trough to trough, as long as you're going to a neighbor. Okay, you can also measure from a point of similar phase to another point of similar phase, and what I mean by that phase is you can see, like, see this point right there where my cursor is. That point there is where the wave shape, the waveform, crosses the x-axis. Okay, it crosses the x-axis, and so you could say, okay, let me start measuring the wavelength there, and then you measure and you go, oh, it crosses there too. But notice that over here it crosses and it's on the way up. Over here it crosses, but it's on the way down. A similar phase would be all the way over to here where it crosses again, but on the way up. So if you measure from this point here where it crosses the x-axis on the way up, and over here crosses the x-axis also on the way up, same phase, then that's also a distance lambda. Okay, so there's lots of ways of measuring lambda. As long as you're going from a similar point to a neighboring similar point on the wave, it's always going to be a distance lambda. Okay, usually I'll say crest to crest, but just keep that in mind that you can do it in you can measure it trough to trough, or like similar phase here to another phase there, like that. Okay, so that's yet another property. So now we have the velocity, we have the wavelength, and there's the frequency. And the frequency, that's a little hard to draw here. So this diagram right there, that's supposed to be like a picture of a human eye looking up at the wave. Okay, and so what you do is you just observe a particular point of the wave, and you just say, how many times does a crest pass by this point per second? Okay, and so you might have, like, within 1 second, you might have 5 crests go by. All right, so 5 crests pass by that point in 1 second. That gives you the frequency. It would be like 5 crests passing by a point per second. Whenever you hear per second, you've seen this already previously in the course. Whenever you see per second, you're talking about a frequency. Okay, so if you just look at a particular point, I mean, don't move the observation to the left or right. Just keep it fixed and just say, how many times does a crest pass by here? Say it's 5. That would be 5 per second, or 5 hertz. Okay, if it's going to be 5 crests pass by that point in a second, then it'll also be 5 troughs. Okay, so it doesn't matter whether you're going to talk about crests or troughs, as long as you just pick one and you say, well, okay, how many troughs pass by? It's basically how many units of lambda pass by per second. Okay, and it could be 5 per second, maybe it's 20 per second, something like that. However many units of lambda pass by per second, that's the frequency. Okay, so that's yet another property of waves. Okay, and for frequency, we will use, let me show you down here, we will use the symbol F. Okay, for some of you that are in chemistry, sometimes they use the symbol nu, which is the Greek letter for N. It looks a little bit like the English V. All right, kind of like a lopsided V. But in this course, we're going to use the frequency. I just mentioned this in passing because, if you've seen this in another course and you go, in this other course, we gave it this different symbol, that's typical too. Okay, but a lot of people will use F for the frequency. So we have the velocity, we have the wavelength, we have the frequency. There's a few more properties. The only other one I'm going to mention right now is the amplitude. Okay, although we don't need it for what we're going to do next. But the amplitude is basically how high the crests are, okay, or how deep the troughs are. Okay, so it's just like the amplitude in an oscillator. It's what's the maximum displacement from equilibrium, and equilibrium in this case isn't a point, it's this entire line, right? It's the entire x-axis. And what is the maximum displacement that this wave is going to have from equilibrium? Well, right here you can see that maximum displacement there, like that. That's the amplitude A. Okay, we could also measure it as it's like the height of a crest, or it's the depth of a trough. Another way to think about it. Okay, and again, that's called the amplitude. All right, so there we go. We've got some properties of waves, and it turns out that lambda, F, and V, that is the wavelength, the frequency, and the velocity, are not independent of one another. They're actually dependent, and they have to obey this formula here. Lambda multiplied by f is equal to the velocity. Okay, and so I'll show you why in just a second. You know, if you have like if you went into the lab, and you will actually, though, you'll have a lab where you do look at waves. You know, you measure the lambda, you measure the wavelength, you measure the frequency, you measure the velocity of the waves. Okay, and if you multiply the the wavelength and the frequency, that had better give you the velocity. Okay, now the velocity of the wave is actually fixed by the medium. All right, so it's not like all waves in the universe have the same velocity, but for a given string with a given tension in it, all waves in it are going to have the same velocity. Okay, or say water waves, I don't know, like waves in your bathtub or something like that. All right, you know, you bob your finger in a tub of water, and you'll see the wavelets traveling out. Those wavelengths will always travel at the same speed. Okay, for that particular situation. So given any particular medium, the velocity of the waves is the same. Okay, that cannot change. So the velocity is fixed. What can change is the frequency or the wavelength. Okay, and the frequency, if the frequency changes, then the wavelength has to also change such that when you multiply the two together, you always get that same velocity. So the velocity stays the same, but the wavelength and the frequency, they can change, but they have to change together in such a way that if you multiply lambda and f together, you're always going to get that fixed value of v. Okay, now I've got some problems like that to try to clarify that, but just to say, you know, look, this is a very innocent looking equation, but you have to, you know, it's not just like a simple little math equation. You have to interpret it correctly in terms of its physics. V is fixed. It's a constant number, but it does depend on the material that we're talking about. Okay, and so the particular medium. Okay, so there's a lot of formulas for V, and they can be derived for different situations. Okay, such as the velocity of sound waves in air. There's a formula very similar to this, and it can again be derived from deeper principles. I don't want to go through all of those. It's not that interesting to look at all of them, but it is good to look at least one of them, one example, because it's kind of like indicative of what gives rise to the velocity in all different mediums. And so if we're talking about a string and you say, what is the velocity of waves in this string? Again, lambda can change, the frequency can change, v doesn't change, and it depends on two things. It depends on, so here's the formula for the velocity of waves in a string. It depends on T, which is the tension in the string. Okay, so the tighter you pull that string, think of a guitar string. Okay, and you know, like how a guitar has the key where you can tighten it, you know, increase the tension and decrease the tension. So if you fix the tension in that string for a given tension, you've got a given velocity. Okay, and the other thing it depends on is mu. And mu is what's known as the linear mass density. It's basically how much mass, I've got it written here, how much mass does the string have per unit length? Okay, something like 15 grams per meter. So if you've got a guitar string, suppose you have a meter of that string and it weighs 15 grams, the linear density would be 15 grams per meter. Okay, because it's a string, it doesn't make sense to talk about the density the way we did with a fluid. Density there was mass divided by volume. But you know, a string doesn't have volume, a string just has length. And so we call it the linear density rather than just a plain old density or a volume density. Okay, and so just like a volume density is mass divided by volume, a linear density is mass m divided by length. Okay, so back to this formula here. If I say what determines the velocity of these waves in a string, it turns out that the tension in the string and the linear mass density. Again, I don't know if any of you have played with a guitar or violin or any stringed instrument. One, you know, the tighter you make the string, the higher the frequency. That's because you're changing the velocity. Okay, and the other thing too is, you know, like on a guitar string, there's 6 strings. It goes from a very thin string, and that would be a string with a very small mu, okay, to a very thick string, which would be a string with a very much bigger mu. Okay, remember mu is mass per unit length. So the thicker the string, the heavier the string, the more mass there is per unit length. Okay, and that mu measures that. So you can think of mu as kind of measuring the thickness of the strings, and T is the tension of the strings. And those two things together determine how fast a wave will travel in that string. Okay, it it, the velocity doesn't fix the frequency or the wavelength. Okay, so to try to help you understand that, with a string, you can grab one end of the string and you can wiggle it slowly, in which case you would have a very small frequency, because very few crests will go past per second, so it'll be a small frequency. Okay, you're bobbing it slowly, small frequency, and then you would have a big lambda associated with it. Same string, same velocity of waves. Okay, but now what we're going to do is we're going to bob it quickly. All right, in which case we will have a higher frequency, okay, and smaller wavelength, but still the same velocity. Okay, so you can actually adjust the frequency, and the lambda, the wavelength, will adjust accordingly, but the velocity remains the same, and what determines that velocity is the tension and the linear mass density. Okay, again, we're talking about a string here, but this would be true even of air. Only with air, it turns out to be the bulk modulus and the volume density of air. Okay, so all waves have some kind of formula like this, which determines the velocity, and once that velocity is determined, it remains fixed, but then that material, that medium, can sustain different frequencies and corresponding different frequencies. Okay, so I hope that one, I didn't overkill it, but we're going to do some problems with this to really nail that theory. The last thing is, let me show you why this equation is true. Okay, and to do that, let me start off by noting or reminding you that the frequency is 1 over the period. Okay, so remember, like if you say, how long does it take one crest to travel from this point to its neighboring crest? That time would be a period, whereas the reciprocal of that, it would be how many crests pass by per second. Okay, so let me see if I can help you with that. If you think of it this way, if you say 5 crests pass by a point per second, that's a frequency, 5 per second. How long would it take just one of them to travel a distance lambda, or to travel, distance lambda, crest to travel? It would be a fifth of a second. Why a fifth of a second? Well, if 5 go by in 1 second, then for only one of them would only have to travel a fifth of that distance to make it so that 5 travel past you per second. Okay, so the frequency and the period are reciprocally related to one another. Okay, we saw that before with oscillators as well. All right, so just keep that in mind. And now if I rewrite the equation, instead of lambda times f, I'm going to write it as lambda divided by t. But then you remember, oh, wait a sec, lambda, that's the distance from one crest to another. So just think of the distance traveled from one crest to its neighboring crest. Let me go back to the diagram. This might help. Okay, so we look at the diagram here. So here we are. Suppose that this crest, remember the whole thing is moving. Suppose we've got this crest here and this crest here at t equals 0. And now we say, okay, let it evolve. This crest is going to travel all along here until it gets to there. All right, so just imagine the crest traveling from there to there. How far did that crest travel? Well, that crest traveled the distance lambda by definition. Okay, how long did it take to travel from there to there? Well, that time would be delta t, would be the reciprocal of the frequency. Why? Well, because the frequency would count how many pass by in 1 second. And so if you've got, say, 5 that would travel from there to there in 1 second, then one of them would only take a fifth of a second to travel from there to there. Okay, so it's the reciprocal. The time is the reciprocal of that frequency. So we'll go back to this equation right here. All right, so v is equal to lambda over f, but rewrite the f as 1 over t. Lambda is how far it traveled. T is the time it takes to travel that distance. Okay, and if you've got a distance divided by the time it takes to travel that distance, that's a velocity. Okay, so this equation here, it's nothing, it looks very different, but it's basically just delta x over delta t, but applied to waves. Okay, so that's where that equation comes from. All right. Okay, so we're ready for our first example. So a guitar string 3 meters long has a mass of 15 grams. Okay, so imagine 3 meters of this string and it has 15 grams. We force one end of the string to vibrate at 250 hertz. So remember, hertz is per second. Okay, so we force one end, we grab one end and we force it to vibrate 250 times in 1 second. If the tension in the string is 1,000 newtons, find the wavelength. Okay, and then for part B, we increase the vibration to 500 hertz, just twice as fast. Now, how long is the wavelength? Okay, so how do you do this? Well, let's put down all the equations that we have above. We had that V was equal to the square root of T over mu. Okay, so that's the velocity of a waves in a string in terms of the tension and the linear mass density. The linear mass density in turn is the mass divided by the length of the string. Okay, and we have those numbers actually. It's 15 grams here. Okay, 15 grams divided by 3 meters, and so 15 grams is kilograms is 0.015 kilograms divided by 3 meters gives you 0.005 kilograms per meter. Okay, so that's how much this string weighs. It weighs 0.005 kilograms per meter, or 5 grams per meter, but we have to work in MKS, so kilograms per meter. Okay, and the tension I told you is 1,000 newtons. Okay, so if you just plug in here for the tension, right here, you plug in 1,000 newtons, and for the linear mass density, you plug in 0.005 kilograms per meter. That's going to tell you that the velocity of waves in this string is 447 meters per second. Okay, so that's the speed of waves in this particular string. All right, and this is kind of typical for these problems. Usually you're looking at about 100 meters per second, or in the hundreds of meters per second. Like the speed of sound is in air. Now I know that air is different than a string, but just to give you an idea, because it's in the same ballpark, it's the speed of sound in air is 340 meters per second. Okay, so for this particular string, the velocity would be 447 meters per second. If this string were like half a kilometer long, all right, 500 meters long, a wave, you vibrate one end, the wave would travel down that string and travel 447 meters in a second. Okay, so this is pretty fast, but again, that's kind of typical for this. All right, so now what I want you to give me is the wavelength, and you say, all right, I've got the velocity, I've given you the frequency, and is there a relationship between velocity and frequency and wavelength? And yeah, it's this equation here, lambda f is equal to v. So, and we have that f is 250 hertz. So if we just rearrange this, because we're solving for lambda, we would have that lambda is equal to v divided by f. So we found out v was 447 divided by 250, and that tells you that the wavelength would be 1.79 meters. Okay, so at 250 hertz in this particular string, the wavelength is 1.79 meters, so roughly 1.8 meters, okay, 180 centimeters long. All right, distance from crest to crest. Okay, now for part B, I said, well, what if we vibrate the string at 500 hertz, which is twice the frequency? So it's the same formula, but we have to be careful. The velocity didn't change. Remember, the velocity is not going to change. The velocity is now fixed. We fixed the tension. The linear mass density is not going to change. The tension is not going to change, so the velocity is not going to change. What changes when you change the frequency is that the wavelength has to adjust. So same formula, velocity is still 447, but now the frequency has gone up to 500. And lambda has decreased to half of what it was above. Above it was 1.79, or rounds off to 1.8. Half of 1.8 is 0.9 meters. Okay, so we doubled the frequency and our wavelength went to half. All right, so I said this before, but now I think you can see it a little bit better. V remains constant, so if you increase lambda, your frequency decreases, or vice versa. Okay, so high frequencies correspond to short wavelengths, and low frequencies correspond to long wavelengths. Okay, they're reciprocally related. The bigger you make lambda, the smaller the frequency is going to be. Conversely, the smaller you make lambda, the higher the frequency. All right. So there you go. This general introduction to waves. All waves do what I just described. It doesn't matter whether they're waves on a string, waves in air, which is sound, electromagnetic waves, which are light, radio waves, microwaves. They all belong to a family of waves known as electromagnetic waves, and so on. And now we're going to look at a couple of properties of waves in more particular situations. Okay, so the first thing we'll look at is what are called standing waves. Okay, so when I first introduced waves above in that diagram, I mean, I didn't show you the string being tied down at either end, okay? And I just sort of said to you, you know, don't worry about how it's tied down. You can think of the string as being like infinitely long, okay? As long as it's been tied down, it has a tension in it. What I described is correct. But you know, when you have to actually do this, like in a lab or something like that, you're going to have to tie down the string at both ends, okay? Why? Well, you know, one end you're going to hold it down, and the other end you're going to apply some kind of a force in order to create a tension in it. And so of course it's been tied down at these two ends. Okay, think again of a guitar. The guitar has two bridges. Okay, it has a bridge down at one end and then a bridge up at the neck, and that's where the keys are. And you know, the string is being held in place by these two bridges. Okay, and the part that vibrates is in between the two bridges. It's not, you know, at the bridges themselves. Okay, and so that's what this diagram here is supposed to indicate. So imagine that you have one bridge right here, okay? Like this is usually a symbol that's given for a wall that kind of hashes there, okay? So this doesn't move. It's a fixed a wall there like that. And here's another fixed wall like that, okay? And in between there's a string, and the dashed line there, that would be equilibrium. So that the dashed line is where the string would be if I don't pluck it. Now imagine that I grab the string in the middle and I pull it up so that it's like that. Up there like that, and then I let go. What's the string going to do? It's going to vibrate. Only the middle part of the string is going to vibrate over here. The two endpoints, this point there and that point there, they can't vibrate because that's where it's being held down. Okay, and when you have this kind of a situation, you don't get just any old frequency. There are only certain frequencies that are going to be allowed whenever a string is tied down at both ends. Okay, and that discretization of the frequencies, the fact that you only get certain frequencies, okay, that's the discretization of the frequencies, that is a result of the fact that the string is tied down at both ends like that, okay? So to show you how that works, let's say that the distance between the two bridges here, okay, is a distance capital L, like that. So from there all the way over to there, that distance is capital L, okay? And though if you ask now, okay, so here's the string here like that, and what's the wavelength? Well, there's the string at one instant in time, and that arrow there is supposed to show that, you know, the string is going to go down and up, down and up, down and up like that. So the middle, picture the middle going down and up, down and up. So here's the string at one time, here's the string at a later time, there's the string at a later time yet, okay? And so the string vibrates up and down in place like that. Well, if you take a look at just this piece in there, just the top piece there like that, that's only half a lambda. And you say, well, why is it half a lambda? Well, because what's a full lambda? Let's go back to the original diagram here. Okay, so a full lambda would be like from there all the way to there, okay? Or conversely, if I start there, a full lambda would be starting here, going all the way from there to there. Okay, so notice you have a crest and a trough. But when you look at the diagram that I just showed you, all you see is a crest. You don't see the trough part. And if all you've got is the crest part here like that, and you don't have the trough part, you've only got half a lambda. Okay, so this diagram here, okay, if you're just looking at the top piece here like that, that's half a lambda. So what would a full lambda be? Well, a full lambda would be if you would extend this past the wall or past the bridge here. So it would go up like that, and then it would go down, and then the trough piece would be over there. It would be like past the bridge. Okay, so if that's half a lambda, a full lambda would be 2L. All right, so that's a little bit subtle. You have to think about that a little bit. So again, you know, if this piece is just the crest part, the trough part would be another L, another capital L. So the crest piece is a distance L, the trough piece would be another L, and the full wave would be the crest plus the trough 2L. Okay, and so lambda 1 is going to be 2L. Why did I call this lambda 1? You'll see in a second that this is the first pattern. The first pattern has the string tied down there, the string tied down there at the two endpoints, and then vibrating in the middle. Okay, and we'll call that n equals 1 and corresponding L1. Okay, now that's not the only way that the string can vibrate. Okay, I could force it to vibrate in this mode by simply grabbing it in the middle and then making it vibrate up and down, but I can also grab it and pull one part of it up and another part of it down like that, and then it would vibrate such that this part comes down while that part goes up. I'll try to demonstrate this with my hands. Okay, so like I have this part here, which is up, it's this way, and the other part which is down like that, and they would vibrate like this. When one goes up, the other one comes down. Okay, so one goes up, the other one comes down. Okay, now here I drew, like I drew the upper part, and then later I drew the bottom part. To not make this diagram too messy, I just drew the one piece like that. But later, what would it do? This top piece would go down there like that, and so it would be the crest here would become a trough here like that, and the trough here would become a crest here. So you would get trough followed by a crest, and then later crest followed by a trough, and so on. So where you see crest, it'll become a trough, and where you see a trough, it'll become a crest at a later time. Okay, now if you look at this, that is a full lambda, isn't it? That's a full lambda in there. And now this one I call pattern n equals 2, corresponding L2, and there that wavelength is a full L like that. Okay, I'll get to this part in just a second. Okay, so that's the second pattern. The third pattern is the same thing, but now I've got three pieces. Okay, now it's a little hard for me to demonstrate this because I don't have three hands. Okay, but just imagine this piece here is going to come down. Well, at the same time, the middle piece is going to go up, and then at the same time that piece goes down. So the two endpoints are kind of going up and down together, and the middle piece is out of sync with the other two going up and down. Okay, so as the two ends here and there go down, the middle piece here goes up. Okay, and it just does that. Now if you take a look at this and you go, well, what's the wavelength of this one? Well, you take a look, you see you've got a crest and a trough, and by the time you get to this point right there, you've already got a full lambda. Okay, so that's a full lambda. Now if you divide the thing into three pieces, you're going to have two pieces are going to be a lambda, and then there's a third piece. So lambda here is 2/3 of the way to the full L. So the full L is all the way along here, and a lambda here is just 2/3 of capital L. Okay, again, a lambda is a crest and a trough, and then you get to there, but you've only had to travel 2/3 of the way across to the other bridge. You only had to travel 2/3 of capital L to get a lambda. So lambda 3 is 2/3 L. Okay, and of course there's an n equals 4, an n equals 5, and an n equals 6, and I think you can see what's going on here. Let me just describe a few of the pieces to this wave. Where it's tied down here, where it's always 0, okay, like there and there, that's called a node. And for n equals 1, the node is at the two endpoints. There's a node at the two endpoints. For n equals 2, there's a node there. Right in the middle there, that's also a node, because that point in the very middle of n equals 2 doesn't move. Like the one side goes up and down, the other side goes up and down, but the very middle point doesn't move. Okay, and so that's a node. So here you have a node there, you have a node in the middle, and then you have a node at the other endpoint. Okay, so there's for n equals 1 there's 2 nodes, for n equals 2 there are 3 nodes, for n equals 3 there are 4 nodes. There's a node there, there's a node there, there's a node there, and there's a node there. Okay, so the point of the string that never moves, always stays at equilibrium, that's called a node. Where the string moves the most, those are called antinodes. So like here where you see my arrow up and down, that's an antinode. This is an antinode. That's an antinode there like that. That's an antinode. Between the nodes, there's an antinode. Okay, we usually don't think in terms much of the antinodes. We usually just think in terms of the nodes. Okay, so this forms this kind of a pattern. I think you can see it now. Okay, where you have 2 nodes at n equals 1. There and there, then 3 nodes, then 4 nodes, then 5 nodes, then 6 nodes, and they're all equally distributed across the entire length L. Okay. Now, lambda 1 we determined as 2L. Let me write that as 2L divided by 1. Okay. And you say, why did you divide it by 1? Well, you'll see in a second. Okay. And then lambda 2 we determined was L. And let me write that as 2L divided by 2. And lambda 3 is 2/3 L. Let me write that as 2L divided by 3. And you notice a pattern. 2L divided by 1, 2L divided by 2, 2L divided by 3, 2L divided by 4, 2L divided by 5, and so on. And you get this formula right here. For, remember, n can be 1, 2, 3, 4, 5, and that's like the different pattern, okay? Just to remind you once again, there's n equals 1, there's n equals 2, there's n equals 3, okay? And I didn't show 4, 5, and so on, but I think you can imagine what they look like. And if you can't, you could just Google for them. They're all, this standing waves, just Google for standing waves. It's all over the internet. It's a very popular topic, okay? But in general, so n is 1, 2, 3. Lambda n for the nth pattern is 2L divided by n, okay? So you'll notice that your lambdas, you don't just get any old lambda. You're going to get either 2L divided by 1, capital L, okay, 2L divided by 1, 2L divided by 2, 2L divided by 3, 2L divided by 4, and so on. You're never going to get like 2L divided by 1.5 or 2L divided by 1.773, okay? It's always 2L divided by some integer. So lambda is discrete. And what discrete means is it means it doesn't come in any old value. Like you can't have a continuum of L's. You can only have certain L's. Only certain L's are allowed, okay? And that in physics is called discretization, okay? And so if the lambdas are discrete and the velocity doesn't change, the corresponding frequencies must be discrete as well, okay? So over here, this equation still works, okay? So lambda f is equal to v, but now I wrote it as f is equal to v over lambda, just divided both sides by lambda, okay? And lambda, we can't just have any old lambda, we must have one of those lambda n's, okay? So fn, which is one of the discrete frequencies, equals v divided by lambda n, and lambda n we just determined was 2L divided by n, and so we get this formula here for our frequencies, okay? So the frequencies themselves are discretized. You get an F1, an F2, an F3, an F4, and F5. You don't ever get like an F1.7 or an F3.9, okay? It's always F of some particular integer, all right? And Fn is equal to n multiplied by v, which is the velocity of the waves in the string, divided by 2L, okay? Where n must be an integer, all right? Now, if you factor out that integer, you'll notice that the lowest frequency, F1, is going to be V divided by 2L. This is usually called the fundamental frequency. F1 here is the fundamental frequency, okay? And then all the other possible frequencies, usually called the harmonics or overtones, okay, those are simply integer multiples of the lowest frequency, okay? So you get, when you ever have these standing waves, you're going to get a lowest possible frequencies, and then all the other frequencies are integer multiples of that lowest frequency. Okay, you can't have just any old frequency. You just get these discrete frequencies, and these discrete frequencies are always integer multiples of some base frequency. Okay, and that's a property of all standing waves. All right, so let's illustrate this with an example. So a guitar string is 2 meters long and made to vibrate. Okay, so you just imagine 2 meters and you just tie it down and you're going to make it vibrate. It's found that the lowest frequency at which the string vibrates is 350 hertz. Okay, so no matter how you pluck the thing, no matter what, the lowest frequency you're going to get is 350 hertz. Okay, if 1 meter of the string has mass 10 grams, what is the tension in the string? So at this point, we go, wow, that's a hard problem. Well, let's just write down all the equations. We'll see how that works out. Okay, so oh, you know what? Let me read the rest of the question before I go on. Okay, so if 1 meter of the string has 10 grams, what is the tension of the string? And part B is, what are the other frequencies at which the string can vibrate? Okay, so I actually answered part B first because that's the easiest one. If the lowest frequency is 350 hertz, that's the lowest frequency, that's your fundamental. The next frequency at which it can vibrate is twice 350 or 700 hertz. Okay, and then the next frequency would be 3 times 350, or 1050 hertz. Okay, so it's going to be 350 times whatever integer. So 350, 700, 1050 hertz, and then it'd be 4 times 350, then 5 times 350, and so on. And those are all the frequencies. Okay, now let's do part A. All right, so even though these are standing waves, so standing means not moving. You know, if you were to look at these waves on a string, you would say, well, I don't see the waves traveling down the string. So they're kind of moving in place, hence the name standing. Okay, and they still, even though they're standing waves, they still have a velocity associated with them, and that velocity is given by v is equal to the square root of the tension divided by the linear mass density. And again, remember, the linear mass density is the mass divided by the length of a string. All right, so we know that the fundamental frequency here is 350 hertz. Okay, and we don't know the velocity. All right, we're trying to find the tension, but you know, to get the tension, we want the velocity, but we don't have the velocity. So if we look here, we don't have the velocity, but we do have the length. Okay, and I don't know if I was totally clear in this problem, but you know, I say a guitar string 2 meters long is made to vibrate. What I mean is the full 2 meters is, you know, from bridge to bridge, the distance from bridge to bridge is 2 meters. Okay, so over here, when you have that capital L, we're going to substitute that with 2. Okay, so we know the fundamental frequency, we know capital L, and we can find that the velocity is 1,400 meters per second. All right, so now we have V. What about the linear mass density? Do we have that? Well, indirectly we do, because I tell you here that 1 meter of the string, if 1 meter of the string has mass 10 grams. Okay, so over here, 1 meter, that's the little L here, 1 meter, has a mass of 10 grams, and 10 grams is 0.01 kilograms. Okay, and that works out to just 0.01 kilograms per meter for the linear mass density. Okay, in these problems, just be careful not to confuse your L's. So capital L is the distance from the bridge to the bridge. Okay, it's the total length of the string that's allowed to vibrate. Little l here is just whatever length of the string you might be looking at for a particular mass. So you'll notice in the problem, I actually give you two lengths. I say that 2 meters of the string are tied down, and then later I say that 1 meter of the string has mass 10 grams. Well, capital L, that's the part of the string that's tied down, that's the 2 meters. And the little l, which is the length that has a certain mass associated with it, that's 1 meter, because 1 meter has 10 grams associated with it. Okay, so just don't confuse the two, because I never try to be tricky in my problems, but I'm going to have to give you two lengths in these problems, because I'm going to have to give you a length that vibrates, capital L, and I'm going to have to give you a length associated with some mass, and that, just don't confuse the two. Okay, so it's 1 meter has associated with it 10 grams, or 0.01 kilograms. Okay, and so that's your mu. Now if you take a look at what you have here, you have V, which we obtained from the frequency, from the fundamental frequency of 1,400 meters, and we have the linear density 0.01 kilograms per meter. Now we can calculate the tension. Okay, so if you take this formula here, square both sides, isolate T, because that's what we're solving for, the tension. T is going to equal mu times V squared. So mu was 0.01, V was 1,400 squared, and that turns out, I went a little bit fast here, that turns out to be 196 meganewtons. Mega is 10 to the 6. So if you actually work this out on your calculator, you're going to find that it turns out to be 196 million. All right, and of course a tension is a force, so it's newtons. So 196 million newtons can also be written as 196 meganewtons. All right, so don't forget mega 10 to the 6. All right, there we go. That's the story with standing waves. Okay, yet another phenomenon that waves exhibit is a result of interference, which we'll talk about at the end of this lecture. But it's a phenomenon which can be described at this point. It's called beating. Okay, and what it is when you have two waves, and they mix with one another, they behave in a certain way, okay? Now, here we have two waves that are going to mix, but they're going to mix and, sorry, they're two waves that are going to mix, but each wave has a slightly different frequency. Okay, so what happens when you have two waves of slightly different frequencies mixing with one another? All right, so I'll mention this again when I get to interference, but right now just think of these two waves that are mix with one another, and whenever waves mix, their amplitudes actually add. Okay, and for the calculus students, I'll actually show you the mathematics of that later. But you know, like if you have one wave and it's trying to put a crest at a certain point in space, and another wave is also trying to put a crest in that point in space, then the two crests tend to build up. Okay, if one wave is trying to put a crest and another one's trying to put a trough, then they tend to subtract. Okay, so this happens whenever two waves meet with one another. But what happens when two waves meet and they have a slightly different frequency? Okay, you get this phenomenon known as beating. And what beating is it's probably best illustrated with musical instruments. So I don't know if any of you play guitar or violin or any stringed instrument. You have to tune them, obviously. And when you go to tune a stringed instrument, you make sure that one of the strings is tuned correctly. And then you can tune all the other strings off of the first string, okay, by pressing down at the correct fret. Now, if you have two strings, and they're supposed to vibrate at the same frequency, and you pluck them both at the same time, the two will simply vibrate together, and you'll just notice a steady note, a steady amplitude note. Okay, but if one string is slightly off in frequency from the other one, you get this beating phenomenon, and what it sounds like is it goes loud and soft, loud and soft, loud and soft. Okay, and when you hear that as you're tuning the instrument, you know that one of the strings that are off, and so you play with the tension to get the strings to the same frequency. And when they're at the same frequency, the two notes together will sound like they have a constant amplitude, okay, constant loudness associated with them. All right. Now, what's going on here is you can actually see it by modeling the waves as cosines. Okay, these are sinusoidal waves. So I didn't give you any of the equations in this lecture. Again, for the calc students, you'll see why they're sine waves in the extra lecture for this section of the course. And you know, one wave will have, you know, some sine wave which looks like a cosine wave, doesn't matter which one you use, a cosine omega 1t, omega 1 being one frequency, and the other wave will have a cosine omega 2 times t. Okay, so the two frequencies are omega 1 and omega 2. They're close. Omega 1 is close to omega 2, but they're not equal to one another. Okay, now I don't want to have to prove this trig identity, but there's a trig identity that allows you to take two sine waves and combine them together. Okay, and here it is. I don't expect you to memorize it, but for completeness, you know, here it is. If you've got cosine one angle, cosine theta, and you add to it another cosine, cosine phi. Okay, so theta is one angle, phi is a different angle. So you cosine theta plus cosine phi. You can actually combine the two together, and you will get two cosine this times cosine that. Okay, so what are the two? So it's like two cosines multiplied together. You're taking two cosines which are added together and you're turning them into two cosines which are multiplied together. And what are the arguments of these two cosines? One of them will be take theta and phi, add them together and divide by 2. Okay, basically that's the average. Okay, so one of the cosines will actually be the average of these two angles. So if one angle is like, I don't know, 44, and the other angle is 46, so 44 and 46 divided by 2 is 45. So it's like the angle in between the two. So this one is the angle between the two. Okay, between the two, theta and phi. It's the average, okay? The other one, however, is the difference. It's half of the difference. Okay, so you subtract the two angles and then you divide by 2. All right. Now, what does this give you? Well, if you take a look at this part here, where you add the two together, so now I put it in terms of omega. When you add the two frequencies together and you divide by 2, you get basically the two waves together will give you a new wave, which is at the frequency of the average of the two. Okay, so the resulting wave has a frequency which is the average of the two frequencies. All right, but on top of that, there's a kind of a modulation. and that's this piece here. This is the part that goes loud, soft, loud, soft. And it is actually also sinusoidal. So it also oscillates over time, but at a much slower frequency. And it's the difference between the two frequencies divided by 2. This piece here is the beat. Okay, and you can Google around for it. Go to YouTube and you can go beat or sound beating or how to tune an instrument, and you will hear this beating. And basically, what it just sounds like is like there'll be like a note, like a constant. Like that. That's when it's in tune. But if there's beating, it would go loud, soft, like that. Okay, and that the modulation, the part that makes it go loud and soft, is this part right here. Okay, and we're interested in that frequency right there. Okay, because this part is just the average of the two. It's like the note in the middle of the two. This part here is the difference, and that's the frequency at which the loud, soft occurs. Okay, and so if you were to actually plot this wave, it wouldn't look like the sine wave that I gave earlier. It would look like a sine wave where at first the amplitude is small, then the amplitude gets big, and then the amplitude gets small again, then the amplitude gets big, and then the amplitude gets small. And then on top of that amplitude going big and small, you can put like this dashed line, okay? And you can see that one of these is basically one beat, and then you have another beat, and then you have another beat. Remember, the amplitude is the loudness, okay? So right here, where the beat kind of ends, that's where it's quiet. And then here in the middle of the beat, that's where it's loud. So it goes loud, soft, loud, soft, loud, soft, and so on. And it does this with a frequency of 1/2. So sorry, the whole thing has a frequency from crest here to crest there. Okay, the actual carrier wave has an average frequency, but the beat is basically half of the difference. Okay, well, there's one more subtlety. If you take a look at the two beats here, okay, and this is probably isn't the best diagram. Down here is what I tried to show it. If you take a look at two subsequent beats, they're almost identical, but they're not. What happens is like where one has a crest, the neighboring beat will have a trough. They've been like one is the flip of the other. Okay, so this is known as the phase, and it turns out that the two beats are like they're out of phase with one another. Okay, so here I show them at 180 degrees out of phase. And the thing is that on an oscilloscope you could see this. An oscilloscope is an instrument for looking at frequencies. Okay, you'll get to play with one in the lab. Okay, but if you have an instrument that looks at the actual waveform, you'll notice that the waveform of one beat is different than the waveform of another beat. But guess what? The human ear can't hear those phase shifts. Can't hear the phase shifts, and so we don't actually hear the beat at 1/2 of the difference. We actually hear it at just the difference. Okay, so that's a little bit subtle. But just remember that humans, when we hear the beating, we will hear it as just the difference between the two frequencies. And the lines here mean absolute value. It doesn't matter which one's bigger than the other. So like you just subtract the two and you take the absolute value of the two. But if you had an instrument like this oscilloscope hooked up to, like, say, a pickup mic to listen in, and you ask the instrument what kind of beating are you hearing, what kind of repetition of pattern you're hearing, well, it would distinguish that this beat is different than that beat. Okay, and it would go, oh, you know what, this isn't, it's not, these are not two different beats, they're part of like the same pattern. And so that would actually happen at half of the difference of the frequencies. So if you're a human ear, you would hear the beat just go from there to there. Okay, and that's it, and then you would see that whole pattern repeat again. But if you were an instrument like an oscilloscope with a mic, you would notice that this beat is different than that beat, and you would have to travel through one quiet to the next quiet over before you would actually get the repeating pattern. Okay, I hope that's clear. Okay, so humans don't hear; they would only hear from one soft to the next soft, whereas an instrument would actually see, oh no, the pattern doesn't repeat there; the pattern repeats across both of these beats. Okay, so all right, let's do a problem which hopefully makes this this clear. Okay, these are actually pretty easy problems. It's just this one subtlety about the fact that the human ear cannot hear a phase, and because the human ear can't hear a phase, your beat frequency is just a simple difference of the two frequencies. Okay, so two strings emit frequency 250 hertz and 252 hertz. Okay, so you just imagine like you have two guitar strings, and you've tuned one guitar string to 250 hertz and the other one to 252 hertz. Okay, what frequency do you hear, and what is the beat frequency? Okay, or I probably should have said what beat frequency do you hear, because I intend to say human. Okay, so the frequency that you would hear, there'd be a resultant note. Okay, it's not like you would hear this note independently of that note. The two notes in your ear, they mix together, and so you can't hear the two distinct from one another, and the two together, combined together, would the frequency you would hear would be simply the average of the two. So it would be 250 plus 252 divided by half, and so you would hear from these two notes, you would hear one note with frequency 251 hertz. Okay? The beat that you would hear on top of that would simply be the difference between the two. Okay, so you just take 250 minus 252. Don't worry about which one's bigger than the other. That's why it's absolute value. And the difference between the two is 2 hertz. So what does that mean? 2 hertz means 2 per second, 2 beats per second. You would hear 2 cycles of loud, soft per second. Okay, so there you go, 2 beats per second. All right. However, if you put this in an oscilloscope, and you ask the oscilloscope, can you show me the repeated pattern? It would actually say, oh, these two loud, soft, this loud, soft, one loud, soft isn't enough. You'd have to actually have two before you have a repeated pattern. It would actually see that that frequency of repetition is 1 hertz. Okay, it'd be slower because it needs 2 cycles of loud soft before it actually repeats the beat pattern. Okay, so just a subtle difference, but again, remember that this is how you calculate it for the human ear. And if you had an instrument and you set the instrument to give you the frequency, it would actually give you that. Okay, all right. So there's the story with beats. All right. Let's move on to waves in 2 and 3D. So implicitly, talking about a wave on a string, we were talking about waves in along a one-dimensional medium, a string. Okay, the wave just simply can travel down the string at some length down the string. It can't go off of the string, and so it's constrained to a one-dimensional object. But if you have waves on the surface of water, bathtub example, and you put your finger in the bathtub and you just bob up and down, you know that you form these circular wavelets that travel out from the middle. Okay, that's a 2D wave because it's traveling along the plane of the surface of the water. All right, and those waves are going to have some properties that are different than the waves on a string because they have this extra dimension along which they can travel. Right, and the same thing is true about 3D. A good example of 3D waves is sound. Okay, so you have sound. Now you can't see the waves in air. And actually the next topic after this is going to be sound, and I'll give a better description of like how sound travels through air in terms of what the air molecules are doing. But there, if you have a sound source here, those waves travel out in a sphere, along a sphere. Okay, and so they're like concentric spheres traveling out from the center where the source is. Okay, and so those are waves in 3D. All right, so not going to do any deep mathematics here. There are some formulas, but no deep mathematics because it's really difficult. Okay, it involves some very fancy calculus that even the calc students we're not gonna do. Okay, so to be able to describe the dynamics of these kinds of waves in 2 and 3D and what they might do, we have to have some kind of a shorthand, and that's what this is. This is a ray. Okay, I'm going to define for you a ray. So imagine that you're looking down on the surface of water. Okay, so this entire sheet here, okay, like the screen on your computer, it's just like, say, a flat surface of water. Okay, and when you look down in the water, there's a wave traveling along the water, and of course you don't see the crests and troughs like that because you're looking down on the crests and troughs. But if you look down along the crest, you would see the crest like a line, and this line here represents a crest. Okay, so again, it's hard to draw, but imagine that the water along this line is higher than the surface, and then behind it is a trough, and the water there is depressed below the surface, and then traveling behind it is another crest, and then another trough, and another crest, and so on. So these are like, this is like a crest front, and there's a trough front, and they're traveling in this diagram to the right. Okay, so if you see my little V's here, each one of these V's shows that their corresponding crest or trough are moving to the right at a constant velocity. So this entire pattern is moving to the right at a constant velocity. Well, this gets really hard to draw in some of the diagrams I'm going to do later, but you could just sort of give a little shorthand and say, you know what, this whole pattern is moving to the right at a constant velocity, and so we draw this line called a ray. Okay, so the ray is basically drawn perpendicular to the crest and trough fronts, and it's an arrow, and it points in the direction that they travel. Okay, so if you wanted to be complete, you would draw the crests and troughs, and that might lead to a very messy diagram. Or you could just draw a ray and without the crests and troughs that you see here. And whenever you draw that ray, you have to picture on top of the ray, or the ray is representing this set of crests and troughs that are traveling as a pattern to the right in the direction of the ray. Okay, so this is known as ray optics, and we'll actually look at ray optics as the very last topic in the course when we talk about lenses and mirrors. Okay, but right now we're just going to do some wave phenomena in 2 and 3D, and for me to draw those diagrams, I'm going to draw them in terms of rays. Okay, so what phenomena do waves in 2 and 3D exhibit? So there's 4 that we can look at. There's reflection. Okay, what happens to a wave when it reaches a surface that it's going to bounce off of? Okay, there's refraction, and this is when a wave travels from one medium to another medium. Okay, so you can have waves actually jumping from one medium to another medium, and the difference between the two mediums is the velocity of the waves. Remember, the velocity of the wave is determined by the medium, so within a particular medium it's one velocity, then there's another medium with a different velocity, and there's an interface between the two media. Okay, and something will happen, and that's called refraction. Okay, another phenomenon is known as diffraction, and diffraction is what happens to waves when they meet barriers. Okay, they actually bend around the barriers, as we'll see. And then there's interference, which I already mentioned in terms of beating. What happens when waves from one wave source meet up with waves from another wave source? They interfere. They mix with one another in a very particular way. Okay, and they enhance themselves. They enhance the crests and troughs in one area. They will annihilate, or they'll tend to decrease the crests and troughs in a different area. Okay, and that's known as interference. Okay, let's go through each of these on their own, and there are formulas, but it's mostly qualitative. All of this, believe it or not, can be proven out of Newton's laws. I know that sounds crazy. You go, how would you even begin to do Newton's laws on this? Well, you would do Newton's laws on all the little particles as they interact with one another, and you can imagine that requires some kind of fancy math, but nonetheless it can be done, and all of the things that I'm going to show you qualitatively can be derived from deeper principles, okay, mathematically. Okay, so let's start off with reflection. Reflection is trivial. There's really nothing to say. When waves meet up with a barrier, they'll simply bounce with the barrier such that the angle of the incoming ray is equal to the angle of the outgoing ray. Okay, so remember, these are rays, so that the wave fronts are actually perpendicular, like the crests fronts are actually perpendicular to these rays. Okay, they'll come in like that, and then they'll bounce out like that. Okay, and if you don't, just ignore the crest, just follow the rays, the angle of the incoming ray is equal to the angle of the outgoing ray. This is exactly the same thing as like what a billiard ball would do if it were to hit the side of a pool table. Okay, and so here we have, say, water, like we're talking waves, water, and this is like the edge of a tub. Okay, the water waves will come in at one angle and they'll bounce out at the same angle. Okay, I should just say how that angle is measured. You'll notice I have a dashed line here. So here's the interface. So here's water, and here's the surface that the waves cannot penetrate. They'll have to bounce off of. Okay, and there's this dashed line here. This dashed line is perpendicular to that interface. Okay, where they bounce, and so this dashed line is known as a normal. Just like the normal force last semester. Okay, it's perpendicular to the surface. Okay, so you measure the incoming angle theta, I guess that's supposed to be an I there, okay? So the incoming angle, you measure that with respect to the normal, and then you'll get an outgoing angle, and that's also measured with respect to the normal, okay? So the rule is very simple. As I said, the theta I is equal to theta R, okay? And again, theta I is the angle that the incident ray makes with the normal, and theta R is the angle that the reflected ray makes with the normal. Nothing very deep here. I don't even know what kind of problems I could ask here, except just to make sure that you understand that principle. It's exactly the same with particles. So again, if you had a billiard ball coming in and bouncing off of the side of a pool table, you know, the billiard ball, the incident angle would equal the reflected angle. Waves do the same thing as particles in this respect. Okay, refraction. Now it gets a little bit more interesting. So what is this refraction? Okay, basically the rays of a wave will bend as they travel from one medium to another, okay? And let's do this in terms of light. So I didn't mention this, but light, visible light, is itself a ray, okay? It's waves. It's electromagnetic waves, okay? And it's a little hard to describe what electromagnetic waves are. It turns out that space, even empty space, it doesn't have to have any matter in it at all, like empty space and outer space, okay, can sustain electric fields and magnetic fields. And it's these electric fields and magnetic fields that are oscillating, okay? And it's that oscillation between electric and magnetic fields that sustains the light, visible light. Also radio waves, microwaves, infrared, okay, which is a form of light that we can't see but we experience as heat, visible light, which we can see, ultraviolet, which is beyond visible, but it's still there. It's what will tan us. It comes. There's a lot of UV that comes from the sun, and if you're out in the sun, you get tan. And then beyond ultraviolet, there are X-rays. X-rays are also electromagnetic. And then in certain nuclear reactions, you get the emission of gamma rays, which are also electromagnetic. These are all the same waves made out of this electromagnetic oscillation, and they all travel at the speed of light, okay? So here in this example, let's just do light rays, okay? So imagine here we have air, okay? And this line is the surface of air and water, and down here is water, okay? So maybe you're like in a swimming pool, and your eyes are like right at the interface between the surface of the water. So there's air on top and water underneath, and you have a ray of light that comes in like this, and it reaches the surface, and what does it do? It bends, okay? And so we have that normal line there like that dashed line, okay? And we have an incident angle here. That's the angle that the incoming ray, see the arrow there shows that it's an incoming ray. The angle that the incoming ray makes with the normal, we'll call that theta A, for theta in the air, angle in the air, okay? And then it gets to that interface, and you'll notice it doesn't travel at the same angle. It actually bends, and it bends towards the normal. And now we have a new angle in there. This is the angle between the ray in the water and the normal, and we'll call that theta water, okay? And so there's one angle in the air, and then there's another angle in the water. They're like that, okay? There's another property known as the index of refraction, N. It's usually given the number N, and it's simply a property of the material. And so air has a particular value for its index of refraction, and water also has a particular value for the index of refraction. Glass has an index of refraction, diamond has an index of refraction, and so on, okay? So these are all different materials which are clear. You could see through. Light can penetrate them. Visible light can penetrate them, but they have this property called the index of refraction, and it actually turns out that the index of refraction is inversely proportional to the velocity of the waves in that material, okay? So there's this speed of light in a vacuum, 3 times 10 to the 8 meters per second, okay? We'll see that number more often in the future. But there's a certain speed of light in a vacuum. But the speed of light in air is slightly slower. The speed of light in water is slightly slower. And so there's this measure of how much the speed changes, and the reciprocal of that speed is actually this index of refraction, okay? And I would just give you that number in a problem, okay? Like, you don't have to memorize these index of refractions, okay? And it turns out that, I went a bit far, okay, you can actually relate the angles in the air and water, and the index of refraction in the index in air and water by this formula here. Okay, and this is known as Snell's law. All right, and so I didn't write it in terms of air. I just said, medium 1 and medium 2 because it applies to more than just air and water, obviously. And so if you take n1 sine theta 1, that must equal n2 sine theta 2. Okay, where n1 is the index of refraction in material 1, and theta 1 is the incident angle in material 1. Okay, and n2 is the index of refraction in the second material, and theta 2 is the angle in the second material. Okay, so this is known as Snell's law, and it basically relates all of these quantities here. Okay, so let's do a problem. We're ready to do a problem now, and so let's do it. A ray travels from air, and by the way, air has an index of refraction of 1. Not exactly, but it's very close. We'll just round it off to 1, okay? A ray travels from air, index of refraction 1, into water, okay? Index of refraction 1.33, okay? The ray makes a 45-degree angle to the normal in the air. What angle does it make in the water? Okay, so the diagram looks like this. So here we have air up here, we have water down here. We have this ray coming in here like that, and it's coming in at 45 degrees to the normal, okay? And then it bends, and it'll actually bend towards the normal. It turns out that the ray bends towards the normal in the bigger n, in the material with the bigger index of refraction. So this theta w is actually going to be smaller than 45 degrees, okay? And so that formula, Snell's law, looks like this. Okay, replacing 1 and 2 for air with air and water. All right, and the index of refraction for air, 1. The angle in the air, 45 degrees. Index of refraction of the water, 1.33. And the angle in the water, we don't know. That's what we're solving for. Okay, and so just plugging into your calculator here, you get 0.707 on the left-hand side, 1.33 times sine of theta w. All right, divide both sides by 1.33. Okay, you get 0.532 is equal to sine theta. And you say, now what do I do? Well, you have to take the inverse sine. Okay, so you get 0.532, and you take the inverse sine of that, and that'll give you theta w. So theta w is the inverse sine of 0.532, and that turns out to be 32.1 degrees. Okay, remember I said it had to be less than 45, and it is. Okay, 32.1 degrees. Okay, so this angle in here is 32.1 degrees right in there. Okay, let's do the reverse of this problem. Okay, the reverse of the above will have the angle 45 degrees to the normal in the water. So here we have water, and the ray is coming in, and that angle in there is 45 degrees. And now when the ray exits, the ray is going to exit at an angle bigger than 45 degrees, so theta A is going to be bigger. Why is it bigger? Because the ray bends away from the normal in the material with the smaller end. So air has a smaller end than water, so this angle must be bigger than 45 degrees. All right, same formula, it's pretty straightforward. So we have n air sine theta air is equal to n water sine theta water. N air is 1, n water is 1.33. Sine theta water, now we know that's 45 degrees, okay, and it's the theta air that we're solving for. And so, just simplifying this, we get sine of theta A is 0.94. Take the inverse sine of that number, and you get 70.1 degrees. So over here, 45 degrees here, 70.1 degrees in the air. All right. Now, at this point, you realize that something could happen here, where if I keep making the theta in the water bigger, we were at 45 degrees and we were getting 70. Let's make it 46 degrees, then 47, 48. If you keep making the angle in the water bigger and bigger and bigger, eventually the angle in the air is going to reach 90 degrees. Okay? Even before this reaches 90 degrees, at some value less than 90 degrees, you're going to get 90 degrees refraction in the air. Okay, and then you say to yourself, what do you think happens if I make this angle here in the water bigger than that critical angle? And the answer is it switches from refraction to reflection. So up until this critical angle here, you get the refraction. When you get to that critical angle, you're actually refracting at 90 degrees. If you go past the critical angle, refraction disappears, and the surface, the interface between the air and the water, turns into a mirror, and you get purely reflection. It's called total internal reflection. So past the critical angle in the water, past the critical angle in the material with the larger n, you're going to get total internal reflection. Okay, it's a really interesting phenomenon, and I don't know if anyone's ever seen this. You can see it in a pool. I remember seeing it when I was swimming many years ago when I was a kid in Italy. You go underwater, and if you look at this, if you look straight up in the water, you can see the air. But as you start to look at more and more steeper angles here, like this, in other words, you start to make the angle with the normal bigger and bigger and bigger. The interface between the water and the air looks shiny. It turns into a mirror, and that's because you've gotten to this point of total internal reflection. Okay, so I call that angle the critical angle theta r for reflection. Okay, that's the point where it switches over from refracting to reflecting. And so in this question I say, what is the critical angle for rays traveling from water to air? Okay, so what is the critical angle? What do I mean by that? Well, that critical angle occurs when the refraction reaches the maximum of 90 degrees in the air. Okay, so to get the critical angle, you still start off with Snell's law, okay, but now in the air, that is in the material with the smaller n, you've reached the maximum theta, and the maximum theta, of course, is 90 degrees, okay, you can't refract more than 90 degrees, so n air is 1, theta air is the maximum it can be in air, 90 degrees, and water still 1.33, and then the theta w, the theta in the water, that's now your critical angle, which I call theta r, okay, for theta reflection or total internal reflection, okay? And so just working this out, you get, 1.1 is equal to 1.33 times sine theta r, so sine of theta r must be 0.752. Take the inverse sine of that, and you get 48.6 degrees. That is the critical angle, okay? So in this diagram here, if this angle here is less than 48.6, you get the usual refraction. The ray will come up to the surface, and it'll actually refract, pass into the air, and bend as it usually does. When you get to 48.6, you're getting right to the point where the refracted ray up here is just skimming along the surface in the air. It's like reached its maximum possible refraction. Okay, if this angle here is bigger than 48.6, this interface between water and air, it no longer can support refraction. It just turns into a mirror. It becomes reflection. It goes from refraction to reflection. And so the ray would come up. So if this angle were bigger than 48.6, say it's 50 degrees, say this angle is 50 degrees, that ray would come in here, and then it would just bounce and go right back down into the water. Okay, and that is known as total internal reflection. All right, so there you go. That's the story with refraction. Notice that you only get total internal reflection when you go from a material with a bigger n to a smaller n. Okay, if you're going from air to water, you can't possibly get total internal reflection. You have to go from the ray has to be trying to travel from the material with the bigger n to the material with the smaller n. Then you can get this total internal reflection. If you are traveling from, if the ray is traveling from lower n to bigger n, it's always going to refract. Okay, so there you go. There's the story with refraction. Okay, next phenomenon, diffraction. This one we'll just do qualitatively. Okay, it's based, you can actually do it mathematically rigorously using Huygens principle, but Huygens principle requires some pretty fancy calculus integration and the like. Okay, but you can. I just want to emphasize that even though I'm giving this to you qualitatively, that you can nail this down quantitatively quite precisely. Okay, so what is this phenomenon of diffraction? Okay, so before we get to waves and what waves do when they go around a corner, let's ask, what do particles do when they get to a barrier? Okay, and so when I say particles, what you could think of is just like, I don't know, like little bullets. Okay, like they could be molecules. Okay, they could be tiny little grains of sand, like any small object which retains its integrity as it's fired along its trajectory. Okay, so if I have a particle here and I fire it towards a screen here like that, so here's a screen, and it just travels and it doesn't reach any barrier, it's just going to go right up to the screen and then just land in the screen. And so you can see here there's a dot. Okay, and then I can fire another particle and it winds up on the screen here like that, and there you go. Leaves another spot, and yet here's another one. And of course, as you keep firing these things, you can see my screen has got all these spots up here. Okay, but then I have this barrier here like that, and if I fire a particle and it lands on the barrier, it might get embedded to the barrier, maybe it bounces back from the barrier. It doesn't matter, it doesn't make it to the screen. Okay, now I'm not going to just shoot a few particles. I'm going to fire a whole bunch of these, so many that I'm going to get a pattern. And the pattern that I'm going to see is that up here I'm going to have a whole bunch of spots where particles landed on the screen, and then I'm going to have this sharp shadow here. Okay, and that sharp shadow corresponds to the edge of the barrier right there. Particles that were fired above that barrier, they make it to the screen. Particles that are below that barrier, that top of the barrier there, they're going to hit the barrier and they're not going to make it to the screen. You get this nice sharp shadow right there on the screen. Okay, this is the story with particles being fired at a screen. Okay, now what happens when you fire waves at a screen and you have a barrier like that? So here we're going to have these crests. So I'm not drawing the rays this time. This time I'm actually drawing these crests. So there's a crest. There's another crest. Crest front. Okay. So, like in between this is where the water's depressed. That's your trough. Here, the line there corresponds to the crest. That's where the water is elevated above the water line. Okay. And so on. Okay. And here's a barrier. And these crests, they get to the barrier. Okay, like that, and they get clipped by the barrier. Okay, now I'm not showing. Maybe some will bounce back here. Okay, they'll be reflected back. I don't want to make my diagram too busy, but it doesn't matter. The crest just makes it like that, and it gets clipped. And then here's a crest that went by, got past the barrier, but look at what happened at the very edge here. It actually, the crest at the very edge, it actually grew a little bit like that, and it's circular there. So this part is supposed to be straight, and then there's supposed to be a little bit of a circular part in there. Okay, and that circular part keeps growing. So here's the crest there later in time, and there's that edge that kind of got clipped, but then it kind of grew. And then there's another piece like that and another piece like that. So you'll notice that it's not sharp there. It wasn't clipped very sharply like that the way it was for particles. The edge of the crest actually kind of grows around, travels around the edge of the barrier, and actually creates this region here, which is the diffracted part of the wave. And it actually starts off with full amplitude there, and then of course as you travel along the crest front, it actually decreases in amplitude until you finally get to that dashed line, and there's no amplitude past that. Now when this makes it to the screen, okay, you can think of this as light, okay, because light, again, you don't see the crests and troughs of light, but they're there. When it gets to the screen, the top part of the screen here is going to be bright. Okay, that means there's a lot of light impinging there. Okay, the barrier didn't affect the amount of light that lands at this part of the screen. Okay, down here where it's past, like where the crests just don't make it at all, the screen is black. It's completely dark. Okay, none of the light makes it there. But you don't get this sharp shadow like you did with the particles. You go from the bright and then you slowly fade to black at the bottom of the screen. In other words, the waves, when they get to a barrier, and they'll actually diffract around the barrier. That's this bending that you see there. And the diffracting causes the shadow to be smeared out. It's not a sharp shadow. It is a smeared out shadow. Okay, the edges of the shadow are smeared out. Okay, so you don't get sharp shadow edges. And this is diffraction. Again, I'm just giving this to you qualitatively, but if you actually had, like, Huygens equation and all that stuff present, and I told you the distance of these, the distance between the crests, in other words, the wavelength, and all the geometry of this, you could actually calculate, how bright the wave would be at any point along the screen there. Okay, so there you go. Now, I just had a single barrier, or like a single edge there. You might say, well, what happens when you have a barrier? So here I have a barrier, and you will actually do this in your one lab on waves. Okay, so here you have a barrier, and here you have these crests. The crests are traveling to the right like this. And when you get to the barrier, at each one of the edges, because there's two sides now to this barrier, there'll be diffraction around that. And the diffraction, the diffracted part of the wave will keep growing until at some point at the other side of the wave, they'll actually like connect back up. And you can see here that, here was the one wave, here's the diffracted part, and there's the diffracted part. They'll actually join up there, and it's kind of like the wave heals itself on the other side of the barrier. It actually wraps itself around the other side of the barrier. There will be an area right behind the barrier, right there, where the wave pretty much has no amplitude, but because of this bending around the corners, it eventually will, the two parts of the waves will eventually meet up, and they'll coalesce, and then you'll always get this kind of little dimple in there, and the amplitude in the middle here will always be less than it is out there, but nonetheless the wave kind of healed itself on the other side. It wrapped itself around the barrier as if the barrier had not even been there. Okay, now that's a barrier like that. What about a hole, which is the opposite of this? Okay, so here we have, a barrier here like that, and barrier here like that, and the waves come in and they've got this hole, and now they diffract, but they diffract, on the other way around the barrier edges here like that, and here like that. Okay, and basically what you get are these circular wavelets that pass through the hole. So the hole changes these like straight line crest fronts into these circular crest fronts, and then they'll travel out and expand like that. Okay, so there's the story with diffraction. The only thing you might say is like, well, what about sizes here? Like, because I didn't give you an equation. What can you say about the sizes of the wavelengths here versus the sizes of the holes, or the sizes of the barriers? And generally, you get the most diffraction, or the most pronounced diffraction phenomenon, when the size of the wavelength is approximately the size of the hole, or approximately the size of the barrier. Okay, so if the wavelength is much bigger than the hole, or much smaller than the hole, you'll get different behavior. Okay, and there's an excellent example of this. You see it every day with your microwave oven. So microwaves are electromagnetic waves. They're electromagnetic waves with a wavelength of about 5 centimeters in size. Okay, so about that big. That's how big the wavelengths of microwaves are. And visible light, the light that we see, now it spans a spectrum, but just roughly speaking, I think yellow light is 550 nanometers. Okay, and nano is 10 to the minus 9, is billionth. Okay, so 550 billionths of a meter. So 5 centimeters is much bigger than 550 nanometers. Okay, now if you take a look at your microwave oven door, you'll notice, I mean, there's plastic, but you'll notice that there's a kind of a metal screen there, and the metal screen has a bunch of little holes in it. And that's how you can see inside. You can see inside because you can see through those holes. And the size of those holes, I don't know, I haven't measured. I'm going to say they're about 1 millimeter in size. Okay, now here's why that's important. A millimeter hole is much smaller than 5 centimeters. In fact, it's, a microwave wavelength is 50 times bigger than that 1 millimeter hole. Okay, and so when it comes to this diffraction here like that, if the hole is much smaller than the wavelength, the wave pretty much doesn't make it through. In other words, yeah, you might get a little bit on the other side, but it's absolutely tiny in terms of its amplitude compared to the amplitude over here. So yeah, there are holes in the microwave oven door, but they're so small that the microwaves can't get through it. Okay, however, the light can, because 1 millimeter holes are much bigger than 500 nanometers. Okay, and so when the hole is much bigger than the wavelength, then the wavelength makes it through no problems, and there's hardly any diffraction, because the diffraction only occurs at the edges, and the edges are far away from most of the wave, because the wave is 550 nanometers in size, and the edges are like they're a millimeter away. Okay, so generally speaking, you're not there's going to be diffraction, but it's not going to be a noticeable diffraction. Okay, and so that's how your microwave oven door works. The holes are much smaller than the microwaves, so the microwaves can't make it through, and they're much bigger than the than light, and so the light makes it through, and it practically doesn't diffract at all. Okay, so there's an example of uh, how the size of the wavelength and the size of the hole or barrier are important. Okay. Okay, last subject is interference. Okay, so interference is when you have just diffraction, and the previous phenomenon is when you have one source. Interference, you have to have two or more sources of waves. Okay, and so as the name suggests, it's when waves from one source interfere with waves from another source. And you might ask, well, what happens? All right. So remember, you've got two sources, and these diagrams are not at all easy to draw because you can imagine overlapping crests and troughs coming from different sources. And they come together and they meet. So let me just sort of describe it schematically. What happens? I mean, imagine that you're in a region of space, and at a particular time, when a crest from one source meets up with a crest from another source. Okay, so just two sources, and one source is trying to put a crest at a particular point in space and time, and the another source is trying to also put a crest there at the same point in space at the same time. Well, what is a crest? A crest is the energy is operating in such a way as to try to, if it's water, like lift the water up. Okay, and so one source is trying to lift the water up. The other source is also trying to lift the water up. The two sources together are kind of enhancing one another. And so one crest plus another crest leads to a bigger crest. Okay, they add together. Okay. Similarly, if you're at some other point in space at some other time, one source might be trying to put a trough there. Another source might also be trying to put a trough there. Trough plus a trough gives a big trough. Okay, they add together. So crest plus crest gives addition of the two crests, and trough plus trough gives an addition of the two troughs. This is what's known as constructive interference. Okay, so both sources are trying to do the same thing at the same point in space at the same time, and they are enhancing one another, and this is known as constructive interference. But as you can imagine, there are different regions of space where at different times, or at a particular time, one source might be trying to put a crest there while the other source is trying to put a trough. Okay, so one source is trying to lift the water up, the other source is trying to pull the water down. What happens? They annihilate one another. They cancel one another out. And so if you have a crest meeting a trough at a particular point in space at a particular point in time, they cancel one another out, and this is known as destructive interference. Okay, if you had particles, like if you were just spraying particles from two sources, the particles could just add up. You have one particle from one source and another particle from another source, you get two particles at that particular point in space. You have twice as many particles. So they just add. Particles can only add, but waves can do this rather amazing thing. They can either add in constructive interference, or they can annihilate one another in destructive interference. Okay, that leads to a rather different behavior for waves than for particles. Okay, by the way, this is how physicists arrived at the conclusion that light is actually a wave. Because how in the world are you going to know that light is a wave? I mean, it's this electromagnetic wave. Like, how are you going to get a handle on whether it's a wave, whether light is made out of waves or made out of particles? And the question is, do they behave like waves or do they behave like particles? If light behaved like particles, then it should only be additive. Two sources of light coming together would only enhance one another because particles can only add. But if you have two sources of light and they come together and they actually give you this interference pattern, you know it's a wave. Okay, now because of quantum mechanics, it turns out that everything has a dual particle wave nature. Let's not go there. I just mentioned it in passing because some people might have heard of quantum mechanics, as part of popular science. But just at this level, you can safely think of light as a wave because it exhibits this kind of interference phenomenon. Okay, so. Let me try to show you a little bit better how you would actually do this experiment. It's known as a double slit experiment, okay? And you can imagine that you have a barrier here and a barrier here, and there's like two holes, okay? So barrier like that and a barrier like that. So I don't know. So imagine one barrier here, and then you just put two holes in the barrier. Okay, when waves travel through this, now I didn't draw the waves on this side, okay, on the left-hand side. I just drew the diffracted waves as they pass through. Coming out of one hole, you're going to have some circular waves coming out because of the diffraction pattern. Coming from the other hole, you're also going to have circular waves. Notice what happens, and I just drew the crests here because, again, I didn't want to overly make this diagram too busy. Okay, notice that here I have a crest from source number 1, so crest from 1. I wrote a 1 here. I forgot to write a little 2 there, but this is like hole number 1. This is source number 1, and there's source number 2. Okay, so here's a crest from source number 1, and here's a crest from source number 2. I should say crest front. And what's happening right at this point right here, that region of space right there? Well, that region of space right there, I have the crest front from 1 and the crest front from 2 meeting one another, and so you're in a situation where crest meets crest and you get an extra big crest. So this is a point of constructive interference. This is also a point of constructive interference, and that's also a point of constructive interference. Okay. Now I didn't draw the troughs because the troughs, again, it would make the diagram too busy, but the troughs are in between the crests. So just imagine a dashed line between these two crests like that. And that dashed line between these two crests, that would be from 1. And then over here, there would be a dashed line in there, the troughs from 2. And what happens? In the same region, you're going to get trough meeting trough right behind this. So here's crest meeting crest, then trough meeting trough, crest meeting crest, trough meeting trough. But there's still constructive interference because you get the two troughs cooperatively working together to produce an even deeper trough. Okay? It's when you're off center here, so there's kind of like a central line here. It's when you're off center that you get into the situation where you have a crest meeting a trough. Okay, and so it turns out that if you just look at the regions of space right in the middle there, which is what we were analyzing a second ago, you're in a situation where you always have crest meeting crest and trough meeting trough. Not just at any particular point in time, but at all time. At all times, as these waves travel, they keep traveling. Okay, nonetheless, in this central region here, you always have constructive plus constructive. A little bit off to the side, you're in a situation where crests are always meeting troughs at all times. And so in the middle you have constructive, and then on either side of that you have destructive interference. And then if you do this analysis properly, still further out you get constructive and then destructive and so on. Now it can't go on forever because you only have up to 90 degrees here, but you're going to have constructive, destructive, constructive, destructive, bands of constructive and destructive right beside one another, and this leads to a very interesting pattern. Okay, and I'll give you an equation for that in a second. Let me just try to show you why you get destructive there. That's a little harder to see, but let's see why. Remember, there is a so here's a crest front. There's a crest front. Hold on. Let me do that again. Crest front here. Crest front here. What's in between those two? A trough, right? So there's a trough right in there. Okay, again, I didn't draw it in there, but just imagine a trough between those two crest fronts. And right there, what's happening right there? That's a trough there meeting from this one over here, a crest. So at this point right there, which is off center, you're getting trough from source number 1 meeting, what's this? A crest from number 2. Trough from number 1 meaning a crest from number 2. You get destructive interference. And notice that that is slightly off center right there. You're in between these two crests from 1, so you're on a trough right in there in the middle. You're on a trough from 1, and this line here is a crest from 2, so right in there, trough from 1 meets crest from 2, destructive interference. And it doesn't just happen at one particular point in time. As this pattern evolves, because remember these crests are moving out, it is always the case at all times that just slightly off center, you've got always destructive interference. Constructive in the middle, destructive beside it, then constructive, destructive, constructive, destructive, like that. Okay, this pattern persists over time, and it is characteristic of waves. Okay, so this was known as the double slit experiment. Why double slit? Well, I called them holes a minute ago, but you could think of them as slits. So basically you have some kind of like a barrier, and you put two tiny little slits using a razor blade or something like that, and they have to be very close to one another because everything has to be on the size of hundreds of nanometers, because it's got to be around the size of the wavelength of light. And you could do this, it's not that bad. Okay, and you shine light through it, and sure enough you get a diffraction pattern, sorry, an interference pattern. Okay, and that interference pattern says light is a wave. Okay, so all right. Let me do the equation for that. Let me describe the equation for that. And so let me first define some numbers that you have to measure. There's the distance between the two holes. So here's a hole here, and there's a hole here. Hole or slit, it doesn't matter which one. So so there's a slit. There's a slit, and the distance between the two slits, and you can measure from the middle to the middle. Let's call that D. That's the distance between the two slits. Okay. Now, if you go straight out along the normal here, we'll call that 0 degrees. And if you're off at some angle, we'll say that angle's theta. So theta is how far off of the center you are. Okay. And then you get these, like I said, these bands of bright, dark, bright, dark. So where we have constructive, if it's light, that's bright. Where you have destructive, if we're talking light, it's dark. By the way, this happens with sound too. Okay. And in that case, instead of bright, just think of loud. And instead of dark, think of quiet. Okay, it's a very difficult experiment to do with sound because sound bounces off of the walls. But I did it once. I actually got two speakers. I measured all the distances right. I made sure that the sound wasn't going to bounce off of the walls. And you walk around the two speakers, and it's remarkable because it's loud, and then you walk a little bit, and then it's quiet, and then it's loud, and then it's quiet. It's a very fragile phenomenon, so it's not easy to do. But if you get it right, it's kind of spectacular, and you realize that sound must also therefore be a wave. Okay, basically instead of slits here, you use speakers. Okay, and the speakers have to be in sync with one another. It's not that hard to do in a lab, but well, it isn't hard except for the fact that you've got to make sure that the sound isn't bouncing off of the walls. Because then if the sound's bouncing off of everything, then it just kind of ruins the interference pattern. Okay, but bright followed by dark followed by bright. Okay, and let's call the middle bright band, let's call that M equals 0. Okay, and then the two bands right beside it, which are dark, we'll call them M equals a half. And on the other side, M is equal to negative a half. Okay. Not that it really matters because this is a symmetrical pattern. Okay, so M equals 0, bright. The first dark is M is a half. The next bright is M is equal to 1. The next one, which will be dark, will be 3 halves. Okay, and so on. Okay, so the half integer ones, they're going to be the dark bands, and the integer ones, they're going to be the bright bands. Okay, so there's a formula for this, and here it is. The formula is D, the distance between the two slits, sine theta, the angle that you're off from center, is equal to M, which is that integer, okay, times lambda, the frequency of the light. And M for the bright bands is going to be 0, 1, 2, and it can be positive or negative, just depends on which side of the angle, which side of center you want to be. Okay, so that's all the plus and minus means. Okay, so if M here is an integer, 0 or an integer, then this is for the bright bands. Okay, same formula, but now just put in a half or 3 halves or 5 halves, these what are called the half integers, then you're going to get the dark bands. Okay, now it turns out that you can actually get an interference pattern with even just one slit. And now that gets a little bit confusing because a minute ago you said, well, it's just going to get, you're just going to have these circular patterns. But actually it's much more complicated than that. And you really have to go back to this Huygens principle and do it properly to see what's going on. So I'll give you a bit of a description of what's going on in the formula, but again, I can't really prove that. This formula here is not that hard to derive, but that's okay. I'm not gonna drive it for you. Let's look at what happens with a single slit. This is known as single slit interference. You would think, oh, you just get the diffraction with the circular, but it's a little bit more than that, because what happens is that the light that travels, say, near one side of the hole will actually interfere with the light that diffracts from the other side of the hole. So the mere fact that the hole has some width associated with it means that light that's diffracting from one part of the hole will actually interfere with light that's diffracting from another part of the hole. So the diffraction is occurring, that is, it's bending around the corners, but it's bending slightly differently from one side than the other side, and that leads to interference, because interference is like two different sources. And it's actually more than just two sources. There's actually an infinity of sources right across the entire hole. Okay, so if you add up the waves that come from all those infinity of sources and the fact that it's diffracting a little bit differently from one side to the other as far as the path differences to the screen, leads to an interference pattern. Okay, so there's two things going on here: diffraction as it goes through the hole, and also interference as the light from one side of the hole diffracted from one side interferes with the light diffracted from a different part of the hole. Okay, so let me give you some numbers here, some variables. A now is going to be the width of the hole. Okay, theta again is the angle off center. So theta equals 0 is right on center, and then off center is going to be, theta. Okay, in this case, you get one big, very bright middle band, very big and bright. Okay, and then there'll be a dark band, and we'll call that dark band n equals 1. And then there'll be a bright band, and then there'll be another dark band, and we'll call that n equals 2. Okay, and then there's another dark band on the other side, -1 and -2. Notice I didn't put any integers for the bright. We're not going to do those. Okay, the formulas for where the bright occurs is a little bit more complicated. So we'll just look at at what angles do the dark bands occur. What angles do these dark bands occur? And the formula for that is this one. And it looks a lot like the previous one, but there's a couple of differences. So yeah, in structurally it looks the same, but let's be very careful. It's the previous one, it was d, the distance between the two holes. Here, a is the width of the hole. Okay, it's the width of the hole. And above I had m, but here I have n. And n in an integer here is actually going to give you the dark bands. So that sometimes causes confusion because integer m right here, integer m gave you the bright bands for double slit. For single slit, integer n gives you the dark slits. Okay, so just don't get confused with that. All right. All right, so let's do an example and then we're done. Okay, so the wavelength of blue light is 450 nanometers. This is approximately right. Okay, so blue light is around 450 nanometers wavelength. Okay, we pass it through a single slit of width 1.5 micrometers. Okay, so now we're going to have to get some of the metric prefixes for the small units. Like when we did the elasticity, we had to have large ones like kilo, mega, giga. Now we're going to have to go to the smaller sizes. Okay, and I'll give you micro in just a second. Okay, so 450 nanometers wavelength. The size of the slit, that's A, 1.5 micrometers. At what angles do the dark bands occur? Okay, at what angles do the dark bands occur? Repeat this, so part B here, repeat, but assume we've got two slits. And the slits, I don't care what the widths are. For the double slit, the width doesn't matter. But the distance between the two matters, and the distance of between the two slits is also 1.5 micrometers. Okay? At what angles do the dark bands occur at, and what angles do the bright bands occur at? And a bit of a vague problem when you say, how many do you want? I said just give a couple of angles for each case. Okay, so let's start off with part A. Part A is single slit. Okay, so here it's a single slit. So we're going to use the formula for the dark bands. So for the single slit, you can only get the angles for the dark bands, and here it is. Okay, and A is the width of the slit. Okay, 1.5 micrometers. Okay, micro is a millionth, 10 to the minus 6. Okay, 10 to the minus 6. So 1.5 micrometers in MKS meters, 1.5 times 10 to the minus 6 meters. Okay, lambda, 450 nanometers. Nano is 10 to the minus 9 billionth. So 450 nanometers, 450 times 10 to the minus 9. And now I move the decimal over 3 to the left, because if I move it 3 to the left, that 10 to the minus 9 becomes 10 to the minus 6. And then the 10 to the minus 6's will cancel. All right, so now what does the formula look like? So I want the angles, right? That's what I asked for. Give me some angles. So sine theta is going to equal n times lambda divided by a. I just took this formula and divided both sides by a. Okay, so I have sine theta is equal to n lambda over a. And I'll just leave that alone for a second. And I got here lambda, which is 0.45 times 10 to the minus 6 meters, divided by a, which is 1.5 times 10 to the minus 6 meters. Notice that, again, why did I go from 10 to the minus 9 to 10 to the minus 6? So that the 10 to the minus 6's would cancel here. Okay, you don't have to do that because, on your calculator, you could work it out. But basically, that's going to give you 0.3. Okay, so when you divide lambda divided by a, it's 0.3. So you get that sine theta is equal to n times 0.3. All right, now what's n? Well, I'm just going to get a couple of the dark bands. So the first dark band occurs at n equals 1. Okay, so if I put n equals 1 there, 1 times 0.3 is 0.3, so sine theta is 0.3. Take the inverse sine of 0.3 and you get 17.5 degrees. So the first dark band occurs at 17.5 degrees on either side. The pattern's symmetrical, okay? So whether it's 17.5 degrees one way or 17.5 degrees the other way, you're going to get the first dark band. What about the second dark band? Well, that's at n equals 2. So you take n equals 2 here. 2 times 0.3 is 0.6. The inverse sine of 0.6 is 36.9 degrees. And there's your second dark band on either side. Okay. For n equals 3, you get 64.2. Same thing, and just put a 3 there instead of a 2. And it turns out to 64.2. If you tried to go past that, you would discover that if you did like 4 times 0.3 is 1.2. The inverse sine of 1.2 is undefined, and so there isn't a fourth band, because you can't go on forever. There's just so many that you can get, okay? Because you can't go past 90 degrees, obviously. Okay, so there you go. There's the last one. It's at 64.2. Okay, and there is no fourth one. All right. Now for part B, we have two slits, and so now we're going to use the two-slit formula. It looks similar, but D instead of A and M instead of N. Okay, let's start off with the light bands. The light bands, we have this, and the M must be an integer or 0. Okay, so rearranging the formula, it's the same approach as before. We have sine theta is equal to M lambda over D, and lambda over D is still going to be 0.3 because lambda is still the 450 nanometers and D is still going to be the 1.5 micrometers. When you divide the two, you're still going to get 0.3. Okay, and now we have, for the bright bands, we have M is equal to 0, M is equal to 1, M is equal to 2, and so on. Okay, so for M equals 0, if you have 0 here, you get, sine theta is equal to 0, and that means that theta is equal to 0. And that always happens. The first bright band is always, the center is always going to be bright for double slit. Okay, so for two slits, you're always going to have M equals 0, sine of theta is equal to 0, so theta must equal 0. Okay. What about the next one? Well, the next one is going to be for M equals 1. And we just did that calculation, so you're going to get the first bright band at 17.5 on either side. Okay, so the middle bright band and then the next set of bright bands beside those will happen at 17.5. And then the next ones past that, again, bright bands will happen at 36.9. Okay, I'm skipping the calculations because they're algebraically the same as what we just did. Okay, the dark bands, though, for double slit, you use the half integers for M. So the first dark bands happen at a half. Same formula, but now for M you put in a half. And so you're going to get a half of 0.3 or 0.15. The inverse sine of 0.15 is 8.6 degrees. So the first dark bands occur at 8.6 degrees on either side of the central bright band. Central bright band at 0 degrees. Beside those are the two dark bands, and they occur at 8.6 degrees on either side. Okay, and then bright bands again, and then the next set of the next set of dark bands past that is M is equal to 3 halves. So if you put 3 halves in there, and inverse sine of 0.45 is 26.7 degrees. Okay, and I didn't show all the details here, but if you want yet the next ones, then you're going to be at M is 5 halves, and that's at 48.9 degrees. Okay, so maybe I should just summarize very quickly here. The very middle, double slit, the very middle, bright. Beside the bright on either side is dark. The angle of the first dark bands, 8.6. Okay, so dark bands. Beyond those dark bands, you have bright bands again. Beyond those, you have dark bands again. Those occur at 26.7, those dark bands. Beyond those, bright, and then beyond those, dark again, and those will be at 48.9 degrees, and so on, okay? And of course, they can't go on forever, but I didn't go past M is equal to 5 halves, okay? I'm not sure you could get M is equal to 7 halves. You could try it and see what you get, but there it is, okay? So there's a story with interference. Okay, so that's it for waves. And for the non-calc students, that's all you need to know for the waves. For the calc students, I'm going to return to the very beginning of this lecture where I had the wave there, and I derived. Oh, I didn't. I not in this lecture. I didn't derive, but I simply uh, gave you this equation here. I'm actually going to derive that. I'm going to show you how Newton's laws applied to a string like this will actually lead to an equation that looks like that. And also, this part I won't fully derive, but I'm also going to kind of explain why you get the velocity as the square root of the tension divided by the linear mass density. Okay, it does require calculus. Okay, and so that'll be the subject of that augmented lecture to this one. Okay, thanks for watching. Bye bye.